here we go. Let's talk about how to calculate a confidence interval for a population proportion. Okay, so hopefully by now we're about 3 videos into this confidence interval stuff. You know the general gist of it. Confidence interval is a way of estimating a population value. In this case, we're going to be estimating a population proportion. Okay, but proportions, they are basically essentially going to be the same process as we did for the confidence intervals for the mean. It's just the formulas are going to be a little different. Well, it turns out that there is a central limit theorem for the sampling distribution of sample proportions. So we talked about the sampling distribution a few videos back for sample means. There's also an analogous central limit theorem for um, proportions. And so this is what it says. I'll just give you the nuts and bolts of it. It says if n times p is bigger than or equal to 10 and n times 1 minus p is greater than or equal to 10, then the sampling distribution of sample proportions. So imagine you have a bunch of groups and you calculate their sample proportion. Proportion means percentage. And if that n times p is bigger than 10, if that n times 1 minus p is bigger than 10, then you say that you have an approximately normal distribution where the mean of the sampling distribution is this p prime, and the standard deviation is this following formula. Okay, so a lot going on here, right? So what they're saying is whenever you have a proportion, a sampling distribution of proportions, p prime is your sample proportion. And in fact, this is also going to be our point estimate for the confidence interval. Okay, so we're going to come back to this. So how do we calculate p prime? It's x, the number of people, or I call it the number of successes, divided by your sample size. Okay, so x is your number of successes. If you're familiar with the binomial probability, it's very similar to that. X is the number of successes, n is your sample size. So think of it in terms of voting, right? P prime is the percentage of people that voted for a particular candidate. Okay, within like a certain sample. So P prime gives you a success rate. On the other hand, 1 minus P gives you a failure rate. So kind of backing this out, if you know a little bit of algebra here, n times p gives you the number of successes, the total number of successes. If you go back and rewrite if you solve that p prime equals x over n formula, n times p tells you the number of x, n times 1 minus p tells you the number of failures. So all that means is that, look, you calculate your p prime. That p prime will be the mean of your distribution. Your standard deviation will be now p prime times the square root. Excuse me, that's a typo. The standard deviation is just the square root of p prime times 1 minus p prime over n. We'll do some examples. It may seem a little confusing now. All right, and as I said before, the important part of the central limit theorem says n times p and n times 1 minus p should be at least 10. And that standard deviation, that sigma p prime, that's called the standard error. And you've heard that term before if you were watching the previous videos. All right, here we go. So this will hopefully clear it up for you guys. Suppose we want to estimate the proportion of adults in the United States that own a smartphone. In a random survey of 100 U.S. adults, 60 of them own a smartphone. What are the mean and the standard error of the sampling distribution of the sample proportion? So here we go. So the central limit theorem tells us that mu p prime, this is the mean of the sampling distribution, is the same thing as the proportion. Well, what is our proportion? Well, the proportion is, remember I said it was x over n. In our case, it's going to be the number of people who own a smartphone. That's what x is. So they told us 60 people own a smartphone out of 100 total people. Therefore, p is just a 0.60, 60%. Okay? So that's your mean. Your mean is the same thing as your proportion. Our proportion is just 0.60. Now our standard deviation on the other hand, is the square root of p times 1 minus p over n. And all that's underneath the square root. So what does that look like for us? Remember, we said p was a 0.60. So this will be the square root of 0.60 times 1 minus 0.60, okay, all over n. What's our sample size? How many total people did we survey? We surveyed 100 people. All right, which looks like a 0.60 times a 0.40 over 100. And let's put that into the calculator. Let's see, do I have my calculator up? Believe I do. Here we go. So I want to take, let's see here, the square root of 0.60 and do it just like this, times 0.40. Do not close up your square root yet. And then divide that by 100 and now close up your square root. Okay, I'm going to calculate that, and 0.049 is what I'm getting to 3 decimal places. So 0.049, and that is our standard error, or our standard our standard deviation for this sampling distribution. Okay, so yeah, they're just showing you here that I didn't lie to you. Okay, our mean is p, which is 0.60, and then they showed you right here how they got a 0.049 for the standard error. Okay, so you know that when it comes to finding a confidence interval, we need a point estimate plus and minus the margin of error. Well, it turns out that the margin of error for a confidence interval dealing with proportions is, we're back to the z distribution. So you take that z alpha over 2 and you multiply it by, that's that sigma p prime. That's that standard error. That's what that is. So that's why we had to go over that in the previous example. Okay, so, and then once you get that, your confidence interval will be your point estimate, which is p prime for proportions, minus your margin of error, and then it'll be p prime plus your margin of error. Okay, so that's how you get your confidence interval. But right now, let's just slow it down. Let's see if we can find margin of errors. Here, they're just showing you a picture reminding you, remember, you have to take that alpha, the remaining area that's not shaded, and have to divide it by 2. That's how you get the correct z-score. And here are some typical z-scores based off of that. If you want to go back to the video on confidence intervals for population mean when the standard deviation is known, I show you how to also calculate these using your calculator. Here we go. Let's back it up. All right. Suppose that a research firm wants to estimate the percent of families living in a city who own a car. Okay, 500 randomly selected families in this city are surveyed. Of the 500 families surveyed, 327 responded yes, they own a car. Find the margin of error for the confidence interval for the population proportion with a 98% confidence level. Okay, so they want us to calculate the margin of error, which involves our z-score of alpha divided by 2, times that weird standard deviation, which was the square root of p prime times 1 minus p prime over n. Okay, that's our formula. All right, so where can we start? Let's start off with p prime. So p prime is x over n, number of successes over your sample size. Go back right here, 327. That's the number of people that responded yes. That's our x. 500 is our n. Okay, so p prime, the sample proportion, will be 327 over 500, which is approximately, let's go 2 decimal places here. So 327 divided by 500. So let's see, 327. Okay. We'll go 3 decimal places. They gave us a 0.654. So it's a point, let me come out here. It's a 0.654. That is our p prime. Now, that means now we also need to figure out our z-score. So if the confidence level is 98%. Hopefully you know this by now. If the confidence level is 98%, that means that alpha is 2%. But remember, we have to take half of that alpha. So we need a z of, let me write it like this, 0.02 divided by 1, which is just asking for a z-score whenever you have a 0.01. Okay? Let me go back a slide. Hopefully this works. And right there, z of 0.01, right there's a 2.326. So that means the z-score we're going to use is a 2.326. Hopefully y'all can see that. Now we have all the information we need in order to calculate the margin of error, or the error bound of proportions, whatever they use. Here we go. Margin of error equals our z-score is a 2.326, and it's going to be multiplied by the square root of our sample proportion. I don't want to keep on doing that. So we're going to take p prime, which is a 0.654, multiplied by 1 minus 0.654 over the sample size, which is 500. Okay? Let's see if we could put all that into the calculator. That's a lot. Okay, so here we go. What is the margin of error? Okay, so it's 2.326 times the square root of 0.654 times 1 minus 0.654, close parentheses, and then divide that by 500. Okay. We work that out, and I'm getting a margin of error of 0.049. And there we go. That's how you get your margin of error. Okay, so here, just a quick slide. Just remember, sample proportion, they're using this symbol P prime. Okay, and then P prime is just simply the number of successes divided by N. The number of successes divided by N, which is your sample size. Okay? All right, you're interested in knowing the proportion of students who plan to major in mathematics for a certain college. Go math. However, there are 50,000 students in total in the college, so it's not practical to collect data from the entire population. And that is a common theme with confidence interval. It's often impractical for you to get the population value. All right, so what do they do? Instead, you take a random sample of 1,000 students, and you ask each student if they plan to major in math. 350 out of the 1,000 indicate they plan to major in math. What is your point estimate, aka what is your P prime? Man, it's X over N. What's X? X is the number of successes. In this case, is the number of people that indicated they want to major in math. There's 350 of them. And we're going to divide that by the sample size, the total number of people that we surveyed, which was 1,000. Okay. We work that out, and you get a P prime of 0.35. Okay. Or 35% of the people surveyed indicated they wanted to major in math. And that's your point estimate. And look, y'all, you take your point estimate, you add and subtract and add your margin of error, and that's how you get your confidence interval for a population proportion. Okay. Once again, this is kind of another central limit theorem question. So as an example, to illustrate the sampling distribution for sample proportions, assume we have a population proportion where 60% of adults in the United States own a phone. We take repeated samples of size 100 from this population, and for each sample, we calculate the sample proportion of adults who own a smartphone. What is the mean and the standard deviation of the sample proportion? Okay, so they're asking for mu p prime, and they're asking for a sigma p prime. Okay. Once again, I don't know why they threw this in here, but this is just another example of the central limit theorem. We said mu p prime is the same thing as p. And P is the proportion of people who own a smartphone in the United States. They told us it was 60%. So therefore, P is 0.60. Write your percents as decimals. The standard error, because that's what the standard deviation of a sampling distribution is the square root of P times 1 minus P over N. What does that look like for us? Well, it's the square root of, we know P is 0.60. 1 minus 0.60 is the other part that we have to multiply it by. Or you could put in 40% there if you're comfortable with that subtraction. Over our sample size, how many total, what's the sample size of our samples? It's the size of 100. So we're going to divide this by 100. All of this is underneath the radical. Let's throw this in a calculator. Clear this out. So we take square root 0.60 times 1 minus 0.60. Okay, we're going to divide that by 100. This is all underneath the radical. All right, we hit enter. 0.049. We're seeing a lot of that, right? 0.049. Okay, so that's just showing you what's the mean and standard deviation of a sampling distribution. Okay. All right. This is just a quick slide. We've already talked about this. That's how you find your margin of error for a confidence interval of proportions. Don't freak out. That Q prime there, I got you. Q prime is just 1 minus P prime. If you're sick of writing 1 minus P, some people write it as Q. It means the exact same thing. All right. Here we go. Suppose that a research firm wants to estimate the percent of families living in a city who have pets. 500 randomly selected families in this city are surveyed. Of the 500 families surveyed, 119 responded yes, they own a pet. What is the error bound for proportions of a confidence interval with 98% confidence level? Okay, aka what is the margin of error? All right, so we've already done this before. Won't hurt for us to do this again. Error bound of proportions, same thing as the margin of error. Okay, so the margin of error, I'm just going to write E. I'll write EBP. The error bound of proportions is you take your z-score of alpha over 2, multiply it by the square root of P times 1 minus P over N. Okay? Whether it's P or P primes, it all depends on what information you're giving. In this case, we're giving the P primes, so we'll input P primes into our formula. All right, so Z alpha over 2. So look, y'all, so the alpha, if the confidence level is 98%, this means that alpha is 0.02, which means that alpha over 2 is a 0.01. Take half of your alpha. So that means that once again, this is our z-score 2.326, which indicates our error bound of proportion. It's a 2.326 times the square root of P prime. Well, we don't know P prime, but we can calculate it. Let me come over here to the blue. P prime is equal to X over N. Of the 500 families surveyed, 119 said yes. The people that said yes, that's your X. 119 over 500. Let's see what that works out to give us. 119 divided by 500. 0.238. So our P prime is 0.238, which means, here we go, we could do the error bound mean, or the error bound of proportions. It's 0.238 times 1 minus 0.238 over N, which is our sample size of 500. Okay, so 2.326 times the square root of 0.238 times parentheses 1 minus 0.238. Close it up and divide that by 500, all within the parentheses, all within the square root. 0.044 is the margin of error there, the error bounded proportion. All right, y'all know the drill. Confidence interval always will be your point estimate minus the margin of error, and then your upper bound will be the point estimate plus the margin of error. Okay. Important, they're just reminding you that, look, confidence intervals are great, but they do have their limitations. For proportions, we can only do this if n times p and n times q are both greater than 10. You have to have a big enough sample size to do these. All right, and those are the steps. You calculate your p prime, which is x over n. You get your z-score of alpha over 2. You figure out your margin of error. And then you calculate your upper and lower limits or bounds. Okay, here we go. Last one. Professor Cope wants to gauge how many students pass this final exam. Students can either score a pass or fail on their exam. He randomly selects 80 students and finds that 68 students passed. What is the 95% confidence interval for the population proportion of Professor Cope's students who passed their final exams? Okay, so here we go. Let's figure out P prime. P prime is definitely important. So P prime is X over N. Okay, X is the number of students who passed. 68 of them passed out of 80. So P prime is 68 divided by 80. What is that as a decimal? So the sample proportion is 85%, 0.85. All right. So now that we know P prime, now we can find the margin of error, which is the error bound proportion, which is z alpha over 2 times the square root of 1 minus, P prime times 1 minus P prime over n. Here we go. What's our z-score? The confidence level is 95%, which means that alpha is 5%. So alpha over 2 is instead of 0.025. So we need this z-score. So our margin of error is 1.960 times the square root of 0.85 times 1 minus 0.85 over n, our sample size, which was, how many total students did he interview or select? 80. Okay, let's see what that is. 1.960 square root 0.85 times 1 minus 0.85, which is 15%, and then we divide that by 80 total students. Enter. 0.078 if we go to 3 decimal places. So this equals 0.078. And folks, we are in business because now the confidence interval for the population proportion is, you take our point estimate of 0.85, subtract away a 0.078, and then we take a 0.85 and we add that same 0.078. And let's see what that gives us. I need the calculator. Okay, so we take a 0.85 minus 0.078. Okay, that's our upper bound, or excuse me, our lower bound. Let's get the upper bound. All right. 0.772 up to 0.928. 0.772 up to 0.928. And what that means is that Professor Cope is 95% confident that the proportion of students, of all students who pass this exam, is somewhere between 0.772 and 92.8%. All right, see you guys in the next video.